SCI Curious ID presents. The universe shouldn't exist. According to physics, the Big Bang should have created equal amounts of matter and antimatter, yet here we are, made entirely of matter. So, what happened to the antimatter that once mirrored our existence? The mystery began in 1928, when physicist Paul Dirac unified quantum mechanics with relativity and predicted the existence of antimatter particles, identical to matter, but with opposite charge.
Behind every moment lies a scientific wonder. I'm Kale, and welcome to Sci Curios, where curiosity meets science.
4 years later, the positron was discovered, confirming Dirac's theory. Ever since, we've known that for every particle in the universe, there should be a corresponding antiparticle. But if equal quantities of matter and antimatter were born from the Big Bang, they should have annihilated each other completely, leaving behind nothing but radiation. Instead, for every billion pairs that destroyed one another, one lone matter particle survived. That tiny imbalance, 1 in a billion, is why the universe and we exist at all. The prevailing explanation involves a process called baryogenesis, the generation of a matter-antimatter asymmetry shortly after the Big Bang. For this imbalance to arise, 3 conditions, known as Sakharov's criteria, must be met: baryon number violation, charge parity violation, and departure from thermal equilibrium. CP violation, first observed in 1964 in kaon decays, means the laws of physics treat matter and antimatter slightly differently. However, the CP violation observed in known particles, such as quarks within the Standard Model, is too small by several orders of magnitude to explain the cosmic imbalance. This implies that new physics, beyond the Standard Model, must exist. Theories range from supersymmetric particles to heavy neutrinos in the Cecil mechanism, which could have decayed asymmetrically. At the frontiers of particle physics, experiments are testing these ideas. At CERN, the LHCb experiment studies tiny differences between matter and antimatter decays in mesons. Other facilities, such as T2K in Japan, examine whether neutrinos violate CP symmetry during oscillation. Any confirmed asymmetry could rewrite our understanding of the universe's origin. Meanwhile, the ALPHA experiment at CERN has trapped antihydrogen atoms to measure whether gravity acts identically on antimatter. If even a minute difference were found, it would have profound implications for cosmology and general relativity alike. Cosmologists suggest that in the earliest moments after the Big Bang, subtle quantum fluctuations may have broken perfect symmetry, creating the seeds of matter dominance. From those infinitesimal differences, all stars, planets, and life emerged. It's a reminder that the universe's very existence hinges on a statistical accident in the laws of physics, a cosmic imbalance so small yet so decisive that it determined everything that followed. The missing antimatter problem is not just about particles, it's about why there is something rather than nothing. Somewhere in the symmetry breaking of the early universe, matter won by the smallest possible margin. And that sliver of imbalance became us. Curious for more? Subscribe and stay curious with SCI Curious ID.
Science is everywhere if you just know where to look. Thanks for watching Sci Curious. Until next time.